The next technique we're going to look at for finding closed formulas for sequences is something called polynomial fitting. Now, before watching this video, I would encourage you to work on the first problem from the in-class activities called Introduction to Polynomial Fitting. That will give you an introduction to the ideas that we're going to use for this particular technique. Okay, and also note that those activities will not be included on the quiz. They are just to help you understand the concepts. So we're going to look at something called polynomial fitting of sequences. First thing we're going to do is try to look at when we can know a sequence has a polynomial as a closed formula. We're going to figure out how to find that closed formula and look at some examples. So our past strategies of dealing with closed formulas for sequences is find some interesting sequences and then find closed formulas for them. We're going to do something slightly different in this case. What we're going to do is think of what a nice closed formula might be and think about what types of sequences might have those nice closed formulas. So one of the nice closed formulas is a type of formula called a polynomial, something that you may have seen in your algebra class. So definition of a polynomial, it looks like some constant plus some constant times n plus some constant times n squared, all the way up to some constant times some n to the m, where m is some kind of number. Now here, n is the variable. We're used to thinking about x as the variable, but here n is the variable since we're dealing with sequences. So the highest exponent of a polynomial is called the degree. In this case, that is represented by m in the expression above. The question we might ask first before delving into the more general problem is, do we know any sequences that have polynomial closed formulas? And if you think back to it, yeah, we do, right? Think simple. We have a couple. If we look at degree 0, where, well, let me see, n to the 0 is 1, so that would just be a constant, right? A sub n equals 5 is a constant sequence. We could think of that as 5 times n to the 0, because n to the 0 is 1. That is that has a polynomial as a closed formula, right? Constant sequence. If we go up to degree 1, that goes up to n to the 1, which means we might have something like, 4n plus 5. That is a linear function. And if we look at some of the terms, 5, 9, 13, 17, that looks familiar itself. That is an arithmetic sequence. So we've actually seen a couple of examples of polynomial closed formulas already. Now let's see if we can extend this to different kinds of polynomials. So question is, how do we recognize a sequence with a polynomial closed formula? Well, let's look at this one. This is an arithmetic sequence. That's a degree 1 polynomial. How might we recognize that as a degree 1 polynomial? Well, we might look at what's called the sequence of differences. And what that means is we find the difference between consecutive terms in the sequence, right? Between adjacent terms. So, for instance, if we look at 7 minus 4, that's 3. Then 10 minus 7 is 3. Then 13 minus 10 is 3. And if we look at it, that we're going to get ourselves a constant sequence from that. So by finding the sequence of differences, we get a constant sequences. So, and this works for any arithmetic sequence. If you take the sequence of differences, you also get a constant. So, looking at that from the perspective of polynomials, if you take a sequence with a degree 1 polynomial as its closed formula, and then take the difference sequence, you end up with a sequence for a degree 0 polynomial. And the question you might ask is, if you have a sequence that has a polynomial closed formula, is the difference sequence always going to be 1 degree smaller? Well, let's look at one. N squared plus n, that's a nice quadratic polynomial. So we get 0, 2, 6, 12, 20, 30, 42, 56, etc. And if we look at that difference sequence, well, 2 minus 0 is 2, 6 minus 2 is 4, 12 minus 6 is 6, 20 minus 12 is 8, 30 minus 20 is 10, then 12, then 14. And what we end up with is the sequence for a degree 1 polynomial. So the answer is yes. And in fact, if we look at the second difference, we get constant, which means that in the case of a quadratic polynomial, it took two different sequences to get to a constant polynomial. And that happens to match up with the degree of the polynomial, which is also 2. Is that a coincidence? Well, no. So to get to a definition, a sequence is called delta n constant if it takes n different sequences to get to a constant sequence. And a theorem which we won't prove in this class, but we'll give some evidence for it in certain circumstances. A sequence has a polynomial closed formula of degree n precisely when it is delta n constant. So we can tell the degree of the polynomial closed formula by just taking different sequences and seeing how many steps it takes us to get to a constant sequence. Now, I should note that this isn't going to work on all sequences. Not all sequences are delta n constant for some value of n. For instance, if we look at this geometric sequence, right, 2 to the n. 1, 2, 4, 8, 16, etc. If we look at that different sequence, well, let's see what happens. 2 minus 1 is 1, 4 minus 2 is 2, 8 minus 4 is 4, 16 minus 8 is 8, then we get 16, 32, etc. And, oh goodness, that is exactly the same sequence as we had before. Well, maybe if we did it again for the second difference. Well, no, we end up with the exact same sequence again. So you can see that finding different sequence, you can take different sequences forever, and it will never change. It will never get down to a constant sequence, which means that this particular sequence, the geometric sequence, is not delta n constant. You can't use polynomial fitting for that particular one. Yeah, that's okay. Can't use the same technique for everything. So let's try another example that we don't know about yet, right? We don't know if it's a polynomial or not. So 3, 6, 11, 18, 27, etc. If we look at the first difference, we get 3, 5, 7, 9, 11, 13, 15. That looks familiar. That's an arithmetic sequence. So if we take a second difference, we're going to get a constant sequence. That means our original sequence is delta 2 constant, and it has a closed formula that is a degree 2 polynomial, a quadratic polynomial. So we don't exactly know what the formula is, but we know it looks like some constant a times n squared plus some other constant b times n plus some constant term c. Right? So a, b, and c are some constants that we just don't know yet. But we're getting closer. We're getting closer. So we know what the formula looks like. How do we find the specific formula? Well, let's plug in some values of n and see if that can help us at all. So remember, this is our original sequence. So for instance, a0 is the first term, which is 3, a1 is 6, a2 is 11, and a3 is 18, etc. So that gives us some information about the sequence. Let's see what happens when we plug in those same values of n into our formula. So remember, our formula is an equals an squared plus bn plus c. If we plug in n equals 0, we get a0 equals c. If we plug in 1, we get a1 equals a plus b plus c. If we plug in n equals 2, we get a2 equals 4a plus 2b plus c. So notice now that we actually have two different ways of writing a0, one from the actual sequence and one from the formula, two different ways of finding a1, two different ways of finding a2, which means that since they represent the same number, we can set them equal. So we know a0 is equal to 3, we know a0 is equal to c, that means that 3 equals c. We know that a1 is equal to 6, we know that a1 is equal to a plus b plus c, that tells us that 6 is equal to a plus b plus c. We know that a2 is equal to 11, we know that a2 is equal to 4a plus 2b plus c, that tells us that 11 is equal to 4a plus 2b plus c. If we plug in c equals 3 into the other two equations, we get a plus b plus 3 equals 6, which means that a plus b equals 3. We also get that 4a plus 2b plus 3 equals 11, which means that 4a plus 2b is equal to 8. Now we have two equations, right? A plus b equals 3 and 4a plus 2b equals 8. We have two unknowns. We can use our techniques from algebra to solve for those unknown values, right? So you know how to solve the system of equations. I'm not going to do it here. You should do it just to practice, but you should get a equals 1 and b equals 2. So let me see. So we got a equals 1, b equals 2. We got c equals 3 from the original equations up there. That means we have all the constants. So an is equal to an squared plus bn plus c. We put in a equals 1, b equals 2, c equals 3. That gives us an equals n squared plus 2n plus 3. So now that you have an idea of how to use these techniques to find the closed formulas, look at the set of activities called polynomial fitting that's on the PDF file included with this video to get some practice.